So today's lesson is about the naming and drawing of alkanes, our simplest hydrocarbons. Things will get more complex after today, but it's super important to understand the basics of this lesson. So the molecules that belong to the member of the alkane family have a general formula CnH2n plus 2. So, for example, we may have an alkane with 3 carbons in it. What should the subscript be for hydrogens? If you're following the formula of 2n plus 2, knowing that n equals 3 allows you to solve for 2n plus 2 by substitution. So if you came up with 8 as the number of hydrogens, you were correct. All alkanes have single bonds between the carbon atoms, and that's the key, that you will see single bonds between the carbon atoms. These, by virtue of that, these are saturated hydrocarbons, which means they'll always have the highest number of hydrogens possible around each carbon. Methane is the simplest hydrocarbon, and that's used in gas stoves and gas furnaces if you have that in your home. Propane's used in barbecues, octanes in gasoline, as well as a number of other different hydrocarbons. Wax is made up of various hydrocarbons, and being in the solid state, they're much longer hydrocarbon chains than the ones that we name. However, we'll explore the properties, the physical properties, later. So, the simplest alkanes, I've got a table here, and I recommend that you copy this down. The table basically has rows for all the way from 1 to 10 carbons. So essentially I would just sketch this out with the headings you see, and we'll do the first couple together, and then hopefully you can complete the table and just check your work after pausing the video. So the memory trick that I've given you here in red, monkeys eat peeled bananas. That's a sentence that can be used to remember the first 4 root names of the simplest alkanes. So M stands for meth. So when we write the name for a hydrocarbon with 1 carbon, we use the root meth because meth means 1. And then we use the suffix of ane. And the reason we use the suffix of ane is because for all hydrocarbons, for all alkanes, the ending of the name is always ane. Now, when you go to draw the structural formula, if you did the complete structural formula, for example, then you would draw your carbon showing all 4 bonds to hydrogens. Feel free to draw condensed structural diagrams. There really isn't a line diagram for methane, so we'll just say not applicable there. Okay, so following the pattern monkeys eat peeled bananas, E stands for eth. So a 2-carbon alkane has the root of eth, which is the root then for 2 carbons, and the suffix of ane, so ethane. So again, if you're looking to draw that, maybe you want to do the condensed now. It's going to take less time. And if you were to draw the line diagram, that's even faster. Boom, done. Moving on to 3 carbons. The P stands for prop. And so a 3-carbon hydrocarbon with single bonds between the carbons is then propane. And that's the gas that's used in barbecue tanks. So if you were to draw this, CH3, CH2, CH3, there's our 3 carbons. If you do a line diagram, just make sure you zig and zag a carbon at the end of each line segment, saturated with hydrogens. And finally, the B for bananas actually stands for bute. So if now I know it's spelled but it's pronounced bute. So if you have 4 carbons in the parent chain of the structure, and these are the simplest ones we're looking at. So for example, CH3, CH2, CH2, CH3. This is then a 4-carbon alkane, 4 carbons, the root is bute, it's all single bonds between the carbons, so it's an alkane. The suffix is ane. The name is butane. If we were to draw the line structure, it could look like that. Okay, so what I'm going to do is go down the IUPAC name column and fill in the root for you to introduce you to those. And then I'd like you to complete the IUPAC name and draw the structural and line diagrams for these simple alkanes. So you can see here that pent, you might think pentagon, 5-sided figure. That'll help you with 5. Hex, 6. Hept is 7, and that would be similar to the spelling of 7 in French. S-E-P-T, set is French for the number 7, so H-E-P-T for 7. Oct, we think octopus. 8. Non, 9, I always think of like nonna, like Italian grandmothers called nonna, and often, you know, they're older if they're getting on in their years, and so perhaps 9 there. And then dec for decade. So you've hopefully copied these down. If you can complete the table and then come back and check your answers, that would be great. Okay, so I hope that you found the line diagrams so much quicker to draw. So the more comfortable you get with those, the faster your homework and test writing will go. So I would really work at learning those line diagrams. Just a comment about how I handled these heptane structural diagrams, structural formulas, and lower. You'll notice that I put the CH2 in brackets and then put a subscript here, meaning that we would repeat 5 of these CH2s in this chain, one right after another, finishing with a CH3, and that would be the total of 7 carbons. So this is carbon 1 and this is carbon 7, and the other carbons 2 through 6 are in the chain between carbons 1 and 7. So another shortcut. Okay, moving on to the alkyl groups. Now, I understand that this next topic can be a little bit tricky, so it's going to take some repetition and practice, and certainly jot down any questions you have. So I've got this new term here, alkyl side groups. Really what alkyl side groups are hydrocarbon branches. So now instead of just having butane, we're going to have carbons coming off of one of those or more of those carbons in butane. And so these are branches or side groups. The technical term is substituent. So what happens if we have a 1 carbon side group? Well, we still follow monkeys eat peeled bananas and the rest of those roots, but the difference is we put a YL after the root, and that tells you that it is a side group. So the way that I've drawn these, everything in blue is a side group, and the green carbon is meant to be the carbon of the parent chain, however long it is. I have not drawn the rest of the parent chain, just so that you understand that this is attaching to the parent chain. So you can see that the CH3 has been called methyl. Meth because there is 1 carbon in this side group, like this piece here is the side group. There's 1 carbon, and so a 1 carbon side group, methyl. So this piece here is the side group, 1, 2. A 2 carbon side group, monkeys eat, ethyl. Okay, what do you think the 3 carbon side group is called? Carbons 1, 2, and 3 attached off the first carbon here. Monkeys eat peeled. P stands for prop. Hopefully you thought propyl. And the last one I have here, 4 carbon side group. Monkeys eat peeled bananas. B standing for but. And YL because, again, this would be a side group. Okay, so that seems fairly straightforward. That's the normal version of these alkyl side groups. Now, is there more than one way to attach a propyl group to the parent chain? Well, you'll notice here when we named the propyl side group that I had carbon 1 attaching to the green carbon. Look how I've drawn the 3 carbon side group for this side group. So here's the side group, There's still 3 carbons, 1, 2, 3, but study the difference between this one and this one here. Notice that now we have carbon 2 attaching to the green carbon, whereas in the first propyl we had carbon 1 attaching to the green. So that's different. The common name, or trivial name it's sometimes called, is isopropyl. And so instead of being propyl, which would mean that the 3 carbons are attached off the first carbon of the side group to the parent chain, the isopropyl means that it's coming off the middle of the 3. So the isopropyl is a very common way that you'll see that side group named. If you were to actually follow the IUPAC naming, I think I forgot to say what IUPAC was. Stands for International Union of Pure and Applied Chemists, and they're the professional organization that makes up all the rules you're learning about how to name and draw these structures. So the IUPAC names this as 1-methyl ethyl. And if you can see how this was constructed, then they're viewing the 2 carbons. Maybe I'll point those out in yellow. They're viewing these 2 carbons here as the ethyl, and then they're saying off the first of those there's a methyl. So this one here is the IUPAC naming of the side group, and the isopropyl is the more common or trivial name. I think most people are really going to find the isopropyl a lot easier, and for sure if you go to the drugstore and buy rubbing alcohol, you'll see isopropyl alcohol. So it is a name that you're going to see around. All right, so other common or trivial names then for side groups that aren't attaching off the first carbon. The rest of these all have 4 carbons in the side groups. You'll notice here 1, 2, 3, 4. So this one's called secondary butyl, or for short, sec-butyl. You'll see sec because it's attaching off the second carbon. And you're probably wondering why it wasn't sec-propyl. Well, there is no other way to have that 3-carbon side group attach other than the first and the second being the middle of the 3. And you'll see that that's common because in our next structure that has 4 carbons, you'll see that in this side group, you'll see 1, 2, 3, which almost looks like the isopropyl arrangement, but there's a 4th carbon in the side group. So you can see how it's similar to the isopropyl in that it's much like a T really, where there's a cap of 3 carbons, and off the second carbon there are then remaining carbons that lead to the parent chain. So if you will, it's kind of a capital T looking at it the other way. So this is then isobutyl. Butyl because there are 4 carbons in the side group. And our last possible arrangement of the 4 carbons in the side group here is where we have a central carbon in the side group, this one here, with then 3 other carbons attached to it. And so this one is called tertiary or tert-butyl. Okay, so very likely you'll want to review those, and if you're looking to check your understanding then of the iso, then I would recommend that you try drawing the iso, let's say isopentyl side group. Okay, see if you can draw that, and pause the video and then I'll have it sketched for you. Okay, so now you can see the isopentyl arrangement. So I have, just like the other iso arrangements, 3 carbons, and coming off the second carbon of the 3 are then the rest of the carbons in the side group. So there's your isopentyl side group. The next section of the lesson involves naming the structures. So the way I've done this, I have this typed series of 5 steps, and I have this piece ready to move. So I've written all my examples down the right hand side, of the page. Now, I realize you're going to copy this series of steps once, and then you'll start with examples underneath. For me, I'm going to run the examples down the right side of the page, and you'll see as I come down that there's quite a few. And this allows me to keep moving the steps down. Now, you'll have them to refer to on your page, but I'd like to be able to point them out to you as we go so you can see which step is which. Might be easier as you're watching the video. So I'm just going to slide this, whoops, just going to slide this back up here. Okay, so in naming organic compounds, and these are really general guidelines that'll take us through the whole unit, with some little details to add as we go. But the first step I've highlighted in yellow, and really that's one that we will be omitting for alkanes because alkanes really do not have a functional group. So for this, we're going to omit at the moment. Okay, as soon as we put a double bond or oxygen in there or halogen, then a functional group will be present and we'll follow step 1. So really for our purposes now, we're really going to follow steps 2 through 5. So step 2, determine the parent chain. So as it says there, that will be the longest continuous carbon chain. Okay, so I've started you off with the C5H12 isomers that you built in the model activity. So we're looking for the longest continuous carbon chain, and hopefully you're thinking of this as being the 5 carbons that run continuously from left to right or right to left. It really doesn't matter which way you number those. There are no side groups, so as long as you run continuously in one direction, that's great. Okay, so I'm hoping you can name this and work a little bit ahead of me on this one. Hopefully you wrote pentane, recognizing 5 carbons in the parent chain, and the ane suffix for alkanes. Okay, so again, we'll start with step 2 for our next example and determine the parent chain. So we're looking for the longest continuous carbon chain. So if I number 1, 2, 3, 4, that will bring me to the end of that run. If I had started at the bottom, I could have come up. That would have worked too. As long as I get 4, I will see that there is a 1 carbon side group off of carbon 2. Okay, so we've determined the parent chain, and we now need, in step 3, to name the parent chain. Don't worry about dropping the E yet. That'll happen when other functional groups are present. So monkeys eat peeled bananas. B stands for bute, and we put our suffix ane there. Okay, step 4, we number the parent chain. I suppose we've already done that. And we're looking to name side groups in alpha order with the correct number. Now, it's worth noting in step 4 that the key is that the side groups have the lowest possible number. And so I purposely numbered this structure from left to right because that would bring this methyl group off of carbon 2. This L should link right up to that B and be all one word. So you'll notice numbers and letters are separated by hyphens and letters run into letters. Now, I actually drew the same structure right beside it, just to point out for numbering, for example, that if you had done 1, 2, 3, 4, this would actually be incorrect. This is not 3-methyl butane. In fact, there is no such thing. What we really need to be doing is numbering this structure from right to left, because that will give the side group the lowest possible number. So in fact, both of these structures that were drawn are 2-methyl butane, meaning they're the same structure. So in step 4, number the parent chain to give the side groups the lowest possible number. Okay, so you'll see I followed step 5 by putting the side groups as prefixes up in front of the butane. Okay, next example. Find the longest continuous carbon chain. There's a few ways you could do this, but when the horizontal is the longest, I tend to go with that one. So we'll notice monkeys eat peeled. P stands for prop. There are single bonds, so propane. And now we have two methyl side groups. So when the side groups are the same, we don't have to say 2-methyl propane. We can say 2,2 dimethyl propane. Okay, so if you had 3 methyls, like 3 of the same side group, it could be tri or tetra. So you'll see di, tri, tetra. Probably won't go any further than that. So moving on to the isomers of C6H14, and then I've gone on and done some other examples. We can continue to name. So I'm going to suggest that you try to follow the rules and name these, and then check in with the rest of the video and see how you did. Okay, so in the first example, we had 6 carbons in the parent chain. Hex is the root, ANE, hexane. In the second example, we have 5 carbons in the parent chain. Numbering from left to right gives us a methyl group off of carbon 2, which is a lower number than if we had numbered from right to left, and so we will stick with this numbering, 2-methylpentane. It doesn't matter in the next example whether you number from left to right or right to left, you'll still have 5 carbons in the parent chain with a methyl group off of carbon 3, and so the name is 3-methylpentane. Also in the next structure, the last example that we can see on the page right now, there are 4 carbons, butane, in the parent chain. And it doesn't matter whether you number left to right or right to left. You'll have 2 methyl groups, one off of carbon 2 and one off of carbon 3. And so we employ that di again for the 2 of the same side groups, putting a number for each side group, 2,3 dimethylbutane. A few more examples here. You can give these a shot. Okay, so in the next example, we have 4 carbons in the parent chain. Be sure to number from right to left to put those side groups off of carbon 2, as opposed to carbon 3 if you had numbered from left to right. And so we have 2,2-dimethylbutane. In the next example, I wanted to show you something where there are 2 carbons in the same side group, and so here's where the ethyl comes in. Monkeys eat. You can see the 2 carbons here in the side group. So there's our ethyl group. 6 carbons in the parent chain, that's our hexane. The ethyl is coming off of carbon 3, 3-methylhexane. Okay, so here's a structure that I'd like you to name, and then when you're finished that one, draw 2-ethylbutane. So go ahead and draw 2-ethylbutane. Okay, so you'll see that I marked up the diagram that I first gave you, and I have redrawn the same structure, except I numbered from right to left that time. And so you'll notice that, yes, there are 6 carbons in the parent chain, so this is definitely hexane. However, depending on if I number from left to right or right to left, I'm still getting both side groups off of carbons 3 and 4, and so it doesn't appear to be obvious which way to do this. So because the side groups are on the same numbered carbons, 3, 4, 3, 4, whichever way I number, now we use this last tip here, that if the numbers are the same, then the lower alpha side group is assigned the lowest number. Now, in my experience, once people try a question like that and use that rule, they think they always use that rule. And I just want to highlight that no, it's only when you number the carbons from left to right and right to left and you're getting the side groups off the exact same numbers. So if the numbers are exactly tied, that's when you follow alpha to go with the lower numbers. So E comes before M, and so this structure on the left is numbered correctly. So we'll go with 3-ethyl, 4-methyl hexane. Okay, hopefully you drew 2-ethylbutane, and so you had 4 carbons, and then off of carbon 2 you drew an ethyl group. Now, I don't know if anything looks odd about that structure to you, But if you were to find the longest continuous carbon chain, would it be butane? I'm going to suggest to you that it isn't, and so I'd like you to study the structure and then rename it properly. Okay, so hopefully you saw that there were 5 carbons in the longest continuous carbon chain with a methyl group off of 3, and so we have 3-methylpentane. Okay, last example here. Hopefully you'll pause the video and copy it down before you check out the answer. Okay, so numbering from left to right gave me side groups off of carbons 2, 5, and 6. And if I numbered from right to left, then I would have had the first side group coming off of carbon 3. So since 2 was lower than 3, I chose left to right. So 8 carbons in the parent chain, there's my octane. I see I have a methyl off of 2 and 6 and a 2 carbon side group, so ethyl off of carbon 5. So just to be clear here, in step 5, we see that it says to name the side groups in alpha order. And so I've put the E before the M because when alphabetizing, we are going to ignore di, tri, tetra, sec, tert. But if you have iso or cyclo, which I know you haven't seen yet, then you do keep the I and the C for the alpha. Okay, last part of the lesson, so just a couple minutes more. Cycloalkanes. So for cycloalkanes, these are all the examples we're going to do. So if you want to pause the video and jot these down, that'll be the end of the lesson. Okay, so you'll see cycloalkanes here follow the general formula of CnH2n. Because we're closing the ring, we're losing those N carbons that are saturated with 3 hydrogens each. And that's why we don't have the 2N plus 2. There's 2 less hydrogens. Okay, so you can see this ring of 3 carbons, right? 1, 2, 3. Whether you go clockwise or counterclockwise doesn't matter until you have side groups. So I know in math this shape is a triangle, the other shape is a square, you'll see a pentagon, but these actually represent cycloalkanes in chemistry. So I know that's always been called a triangle, but now we're going to call it a cyclic structure of propane. So the prefix is cyclo, cyclopropane. I'm pretty sure you can name the next 2 structures, so give that a shot. You'll probably be good with the rest. Just check in with the video when you want to correct your work. Okay, so just checking your work now. For the square, hopefully you numbered 1, 2, 3, 4. Whether you went clockwise or counterclockwise doesn't matter when there's no side groups. It doesn't even matter where you start numbering. Cyclobutane. Same with the pentagon, cyclopentane. That time I numbered counterclockwise. Now, when we get to the 4-sided figure with then the side group here, the methyl group, the carbon of the ring where the side group is attached is always carbon number 1. I'll say it again. The carbon of the ring where the side group is attached is always carbon number 1. Now, when there's only one side group in a cycloalkane, then we don't number the side group. There's only one. If 30 people in the room draw methyl cyclobutane, they're all going to draw a square with a line coming off one of the carbons. And that will always be carbon 1, and so everyone's drawing the same structure. Now when we get to the other one here that looks a little bit like a riding horse maybe. Now there's a question. Do I start with the carbon of the box that has the ethyl group here as carbon 1 like I did? Or perhaps the methyl should have been carbon 1? Well, if I numbered the way I did, that puts the ethyl on 1 and the methyl on 2. And I have to number counterclockwise here. I have to number counterclockwise. If I had started at 1 where the ethyl is and gone clockwise, that would have put the methyl off of carbon 4. So 1, 4, no way. 1, 2, that's lower. Now what if I had started, and I'll show this one in green, what if I had started here as carbon 1 and went this way, 1, 2, 3, 4? Well, my side groups are still off of carbons 1 and 2. So when the side groups are going to be off of the same numbering, So just like before with branches on alkanes, you put the lower alpha psi group with the lower number, and that's why I went with 1-ethyl. So E comes before M, so there's 1-ethyl, 2-methyl, cyclobutane. And the last structure here was a little bit odd looking. The parent ring system is the longer or larger ring. So in this case, 6 in a ring compared to 3. That makes the cyclohexane the parent ring system. And that means that this is a psi group. What is the psi group? It's 3 carbons in the psi group, but it's not propyl or isopropyl. These 3 carbons are in a ring. So cyclopropyl. Now I purposely highlighted or changed the color for the YL. So just wanted you to notice that this 3 carbon cyclic structure is being named as a psi group, and that's why we have the YL. Okay, I'll see you in class.